All right, welcome back everyone, and what we're going to be doing right now is taking a look at how to find the midpoint, not in 2 dimensions, but in 3. And it might sound a little intimidating and also look a little intimidating, but I promise you, if you follow the steps, you're going to find it's just as easy as doing the midpoint formula in 2 dimensions with just one extra thing added on top. All right, so perhaps for some of you, you've never seen a Cartesian coordinate plane expressed in 3 dimensions. So we're used to just seeing this kind of, all right, we have x here going left and right horizontally, and then y going up and down vertically. In 3 dimensions, it changes a little bit. If we want to represent 3-dimensional space, we have to basically write out a Cartesian coordinate plane or a graph in 3 dimensions on a 2-dimension surface, in this case, my iPad. So what we're going to find is that this one going out to this direction is going to be our x, over here is going to be our y, and then going upwards is going to be z, or z for, depending on which alphabet you use. So you write it typically as same order, x, y, but in this case we have this z coordinate on top. So whatever our coordinates are given, we're going to be moving this direction first, this direction second, and this direction third to give us a value in 3 dimensions, right? So now let's take a look at an example problem and see what exactly this looks like when a question asks us to represent something in 3-dimensional space. All right, so in this example, we have a cube or a cuboid. Kind of looks like a cardboard box. And you're going to see a lot of different numbers there. A, B, C, O, A1, B1, C1, O1. It's going to have dimensions 4 by 5 by 2. We have the vertices on the following coordinates, 4, 0, 0, 4, 5, 0, 0, 5, 0, and 0, 0, 0. So that might seem like a lot. But luckily, we're given a graph of this thing to kind of help us establish a base of what we're doing for our first time through this. So let's go ahead and let's start labeling those points. Now, first one is going to be our easiest point, and that is going to be our origin O, which is 0, 0, 0. That's going to be right here. And that's going to be a value, that's going to be our origin O. So now I have other vertices. I have A at 4, 0, 0. So remember that we're going to be moving in the x direction, the y direction, then the z direction. And let me go ahead and label these x, y, and z. So 4, 0, 0, I have a 4 unit movement in my x and then nothing else. We are A at 4, 0, 0. Then I have B at 4, 5, 0. So you can see that these share the same x value, which means we're both coming out here. But then for B, I have a 5 unit movement in my y, but then nothing in my z direction. So right here is going to be my B. Then my C is 0, 5, 0. So I'm not moving in x at all. I'm only moving in y. So I have 0 movement in x. Then I'm going to move over to the right on my y-axis 5 units. And I'm not moving up either because I have a 0 value for my z, which means that this right here is going to be my C. Okay? So what's often common in these types of problems is that I might actually want to call this one up here A prime. I might want to call this one up here B prime, and this one up here C prime, just to denote that, hey, it's, it takes on very similar coordinates as A, B, and C, of course, with the movement up and down on the z-axis. But I'm going to go ahead and just denote that with a little bit of the prime notation just to differentiate it for now. So what I notice is that I do have dimensions 4 by 5 by 2. And that makes sense because I've seen 4, I've seen 4, I've seen 5, and I've seen 5. So that kind of takes care of this whole 4 by 5 part. So when I say by 2, that is meaning that I have a height, that this box has a height, this cuboid has a height of 2. What does that mean? Well, it means that A prime and all my other coordinates here, I can actually assign values to. So if A is going to be 4 in the x, and I still am not moving left or right at all from this axis. So my y still has a 0 value. So I'll have 4 and then 0. But again, I have a height of 2 given that this box is 4 by 5 by 2. So that means my z is going to have a value of 2. I'm moving 2 up. It's going to be a very similar thing as my b prime here. So I'm going to go ahead and just write this a little bit further out. So b prime is going to have a value of 4, 5, and then 2. And then c prime, well, I have no movement in the x. I do have movement in the y, which again, C moved by 5, so this one's also going to move by 5. And then I went up by 2. Okay, and just as a little bonus, if I wanted to have O prime, again, I had no movement in x, I had no movement in y, but again, I had a height of 2. So there we go. Now we kind of have coordinates listed out for all of this. So we went ahead and took out part A. So we sketched the coordinate system in 3D of the cuboid, and we determined the coordinates of the vertices A1, B1, C1, O1. So you'll notice that I use the prime notation, and then the problem is using a subscript of 1, A sub 1, B sub 1. Either or is okay. You're just denoting that it is related to A, B, or C, but it's just a little bit different because in this case, it's right on top of it. It's going to be kind of that same exact coordinate, but just given a height element to it, a height coordinate. So now let's go ahead and let's determine the coordinates of M, which is the diagonal from A to C1, or in my case, A to C prime. So the question is, how the heck do I get a midpoint of this green line? So what's important to note here is that I'm going to have some different coordinates, and the ones that I'm taking into consideration are going to be A, because that is going to be the starting point of this line. And what are my coordinates of A? Well, it's just 4, 0, 0. 4, 0, 0. My other coordinate is going to be C prime or C1, depending on which way you want to write it, and that's going to have a value of 0, 5, 2. Now, when we worked in 2 dimensions, we simply took the average of the x's and the average of the y's, and that gave us the coordinates for the midpoint. It really is no different here, except the only difference is that I now have a z coordinate. So what you do is the same exact steps. You find the average of the x's, you find the average of the y's, and now you also find the average of the z's, and that is going to give you the midpoint in 3 dimensions because you're taking the x dimension, the y dimension, and then the z dimension. So what that looks like algebraically is I would have my midpoint here, M, and that's going to be equal to, all right, my average of x's. In this case, I have 4 plus 0 over 2. My average of y's, I have 0 plus 5 over 2. And then my average of z's, which is 0 plus 2 all over 2. And what it's going to give us is this midpoint of, let's see here, 4 plus 0 over 2. That's going to give us 2. 0 plus 5 over 2, that's going to give us 5 over 2, or 2.5. Then I have 0 plus 2 over 2, that's going to give us a value of 1, and that will end up being the midpoint. So what you'll find is that if you move 2 units in the x direction, then 2.5 units in the y direction, and then 1 unit in the z direction, you will find the midpoint right here on this green line going across. Okay, so it's no different than what we found by doing the in 2 dimensions. The only difference is that we have a z coordinate, so we just do it a third time. We find the average for this third coordinate, and that's the only difference. It's the same thing, just one extra average that we have to take into account. So part C is asking us to explain whether or not you would expect AC1 or AC prime, which is what we just did, if that midpoint is going to be the same midpoint as A1 or A prime down to C. So would these 2 diagonals have the same midpoint? And the answer is, well, yes, because these are just diagonals in a box. And if they're going in this direction, again, you can mathematically do this by plugging in the coordinates into the midpoint formula and solving. Yeah, and if you also just realize a little property from geometry, well, the intersection point of 2 diagonals of a rectangle is really just going to divide each of those diagonals in half. So by a property of geometry, we can just say that, yes, they are going to have the same midpoint, or at least they should. It would be weird if they didn't, especially in a textbook problem. Maybe there's a manufacturing defect or something. But you'll also find that if you plug in the coordinates for A prime or A1 and C as well, which was right here, back into our midpoint formula, you'll also get the same exact answer. So there'll be 2 different ways to prove that, either by using the properties of geometry or by using the midpoint formula. So there you have it. That is how we can use the midpoint formula. And it is the same idea as finding in 2 dimensions, except that we just have a third coordinate z that we need to take into account. So again, it really is no different, except it just looks a little bit more complicated and strange. But if you break it down into the components, label your diagrams appropriately, and then take things step by step, you will find that you get the right answer every time. I hope this helps, and in the next video we'll be going over the distance formula in 2 dimensions and also 3. All right, see you there.